let's going. So I'd like to talk today about trees, branching, and random walks. So, but I'm going to start with a game that some may well come across. Is a nice one to this source of discussion about probability, and that's a classic.
So the car and the goat show. So we've got two goats and one car hidden, and the objective is to find the car. So first of all, you're going to pick a car, pick a door, and you hope the car's behind it because you don't know. So I'm going to pick the one on the right-hand side. So clearly there's 1 in 3 chance that I choose the car, right? I mean, there's 3 doors. I don't know which is which. But now the host is going to reveal one of the goats behind one of the other 2 doors. So there he reveals a goat behind the first door. That's one of the doors that I didn't choose. So now the question is, do I stick with my first choice or do I swap? Well, you might think, well, look, there's 2 doors. There's a car and there's a goat, so it doesn't matter. It must be just 50-50. Who cares? Well, I'm going to swap. So I'm going to move my choice to the middle door. Did I win? Damn it. No, I didn't. I got the goat. The car was behind the one I chose first. But actually, I mean, this is an exercise you can try if you've not seen it before. It really is the best policy to swap in these conditions when the host always reveals a goat behind a different door. It actually is going to double your chance of winning to 2/3. So you might want to discuss that or think about that in your classes. So the key thing here that appears throughout probability, and often many of the paradoxes, so-called paradoxes in probability, are often to do with conditional probability. So the key thing is extra information matters. It changes the odds, and you've always got to be conscious of that when you're doing probability. Okay, so that's my little intro game. So now let's suppose that we going to play another game, a fair game this time, and we're going to play it repeatedly. Each game is going to be independent. The probability we win the game, let's suppose it's a half. The probability we lose the game, it's a half. And we're going to keep track of the wins versus the losses. So I'm going to define a process starting at 0, at time 0, and then at time n, it's going to be the number of wins minus the number of losses I've had after the n games that I've played. So it's going to keep track of my winnings in a sense. So what would a typical trajectory of this game? It's a random game, but if we look at a typical realization, so maybe we won, then we lost, then we won 2, then we lost 1, then we won 3, lost 2, won 1, and so on. So this we get a function that we're drawing with time on the x-axis and our score xn on the on the y-axis. So this is what's known as a simple random walk, and this is like a probabilist staple. And it's what's known as a stochastic process. So it's a process that's evolving in time. So of course, this is related to something that you'll cover, I'm sure, in school with your kids. Is the binomial distribution pops up. If I want to know what's the probability that I've got my position at time n is k, so I've won k, the wins minus the losses is k after n games, then this is just given by binomial probability, and it's a 50-50, so it's n choose u, a half to the n, where u is the number of wins that I need to get to final position k. And that's easy to work out because the number of wins, u, plus the number of loses has got to be the total number of tosses, n, and we know the difference between the wins and the losses, that's the position, has to be k. So this is just a kind of, it's a binomial probabilities, but it's a slight modification to get the correct position. So random walk, it crops up naturally. It's one of the first distributions you learn about in probability, the binomial. Of course, we could do this for a bias game as well. And instead of a fair coin, we could have the probability of winning the game was P and losing the game was 1 minus P for some P in 0, 1. And then we just get the more general binomial probabilities, n choose u, this is n factorial over u factorial, n minus u factorial, p to the u, 1 minus p to the n minus u. And this will give us the distribution for the position of the random walk at some time n, any time n. So that's the simple random walk, which I'm going to talk a little bit about throughout the talk. So now let's think of a related question. Suppose we go back to a fair coin and we toss repeatedly, then we might ask, well, how many tosses on average does it take until you get the sequence head tail? Okay, so simple question. Again, you can muck around with this in class or in practice. So actually we can rephrase this in terms of a simple random walk. So if we think of a head is a win, and that's moving up 1 for the random walk, a tail is a loss, and that corresponds to jumping down by -1 in the random walk. So getting a head tail when we're tossing our coin is the same as getting an up followed by a down in the path of the random walk. We want to know how long on average until we first see this sequence, this bit of shape in the path of the random walk. So for example, if we got a tail and then a head on the second, head on the third, head, tail, and so on, that would correspond to this realization of the random walk. So we lost, we won 3 times, we lost, we won, lost, and so on. So when do we first get a head tail? When do we first get a head tail in this sequence? Well, it's here. It's after 1, 2, 3, 4, 5 tosses. We've first got the head tail has appeared. So in this realization, if I call tor ht the number of tosses until we first get the sequence head tails, in this realization, this random time is 5. Of course, if we toss the coin another time, we get a different realization, we get a different time for tor head tail. So and here you can see actually there were 3 occurrences of head tail in the sequence so far. Of course, it carries on after this. So that's 3 of these little B's separated. So what is the time on average? If we took the average of all of that time, it's 4. Why should it be 4? Actually, it's quite easy to see. First of all, we have to wait for the first head, and it's actually a mean of a geometric because there's a probability of half of getting a head. So the average time until the first head is just 1/2. It's 2. And then all we have to do is wait until the next tail and we're finished. Because if we've got a head, here's the first head. If we don't get a tail, well, we've got a head again. If we don't get a tail, we've still got a head. So the next time we get a tail, we've automatically got head tail and we're finished. So we just have to wait for the first head and then wait for the next tail and then we're done. And that's another 2 tosses. So it's 2 plus 2. So, okay, dead easy. So now let's ask the same question, but for head tail. But for head. How long on average to get the sequence head? Well, you must think, well, it must be 4, right? I mean, head, tail, head, come on. Heads and tails are all the same. So in this case, we're looking for a bit of path that's 2 wins on the trot, right? Up and an up. So again, if we look at our particular realization of tossing heads and tails, and we think of it in terms of the path of the random walk, we had a head here the first time. So the time tau till we first got a head is 3 in this realization. We also got a head on the 4th toss and also 1 over here. And you see they're overlapping here. That's significant. So yeah, it must be 4, right? The average time must again be 4. No, it's 6. Surprise, surprise. This can, I mean, some people might think, oh yeah, okay, no. But it's surprising to many people. Why is it suddenly harder and take longer to get head than head tail? Well, here's the quick explanation. You wait for the first head as before. So now you've gone the first head of your sequence. If the next one is head, great, you're finished, done. But if you get a tail, you've stuffed up. right? You have to go back to the beginning. It's like snakes and ladders, right? If you get a tail, you've got to wait for the first head all over again. So it's much worse and harder than waiting for the head tail. So that's the intuition. Of course, if you didn't believe me about this, or something you can do with your students, you could simulate or play for real the game many times, record the number of tosses until you get the first head each time on each realization, repeat that and take the sample average. And we know that the sample average should get closer and closer to the true average as the sample size grows. In fact, that's an example of the strong law of large numbers, which is one of the cornerstones of probability theory. If you take a sequence of independent, identically distributed random variables, you add them all, add up n of them, divide by n, that converges as n tends to infinity to the actual mean. And that happens always with probability 1, not some of the time, not a quarter of the time, always. So that's a very important, one of the cornerstone laws of probability. You could check it by using this. This is kind of what happens in a lot of situations in statistics, that you want to estimate something, you can do a lot of sampling, and then you can use that sampling to get averages, to get estimates. So this is an important method. Monte Carlo Markov chains is kind of based on similar ideas. So can we see what's an argument? How could it actually prove that result? Rather than just relying on simulation, what would probability offer to actually prove that average time is 6? So there's actually a theory called Martingales, which is all about fair games. And this is a very powerful theory that's used throughout probability. And I'll give you one example. This is one example where you can apply it. So there's a very nice argument. So suppose a new player is going to arrive every time we toss a coin. So for each new coin toss, a new player is going to arrive. And whenever they arrive, they're going to bring $1 with them. So the number of tosses we've had is the number of players that have arrived, is the number of dollars in the system, brought into the system. So whenever a player arrives, they're going to try and bet all the money on getting head-head. So they bet their first dollar, the dollar they come with on the first toss that they observe, agreeing with the first toss, for the first coin that they need in the sequence, in this case a head. If they get a tail, they lose and leave with nothing. If they get a head, they double the money, get $2 and carry on playing. So note on average, they still have $1 after the first game they've played. So it's totally fair. The probability of half, they've got nothing. Probability of half, they've got 2. So they've still got $1 on average, the same dollar they arrive with. So it's a fair game. Now, if they carry on, so if they got ahead on the first toss, they double up. They bet all the $2 on the second toss, agreeing with the second in the sequence. If they lose and get a tail, they leave with nothing. If they do get the head, they double up, they've got $4 and they stop playing. So again, on average, they've got $1 if they stop playing after 2 tosses. So it's a fair game. So because it's a fair game, the average money out should be the same as the average money that comes in, should be the same as the number of tosses taken, should be the same as the number of players to arrive. So now the argument is, well, if we stop, we use this stopping time exactly when we first get a head-head, then we should have, what should we have? If we stop when we first get a head-head, well, the money out, or the total winnings in play, another way of thinking about it, if we stop when we first get a head-head, then there's 2 gamblers that have still got money. There's the one that's just got the second head, and he's on $4. But there's also the gambler that's just arrived that won on the first head, and he's got $2. So there's $6 in the system. But how much, $6 in winnings in the system, but how much came in? Well, the average money that came in, it corresponds to the average number of players that arrived, which is the same as the average time. So there's the proof. So the average time to get the head-head is the same as the average number of players is the average number of winners, because of this fair game property. So say this is an example of martingale theory. So that's a way you could prove that result without having to do simulation. So just to give you a little puzzle for homework, now suppose we've got a monkey. Okay, no monkeys will be hurt, but the monkey is sat in front of a restricted keyboard of lowercase letters, and he types at random on his keyboard. He's trying to write Shakespeare. You know, he thought, I'm just going to write the works of Shakespeare. But actually, well, we'll start with a simpler target. So how long on average until the monkey first types abracadabra? So he's typing at random. He's not really a clever monkey. So he's got 26 lowercase letters. He chooses each of them with probability 1 on 26, and each choice is independent of the last. How long on average until he gets abracadabra? Answers on a postcard. Well, it turns out to be 26 to the power 11 plus 26 to the power 4 plus 26. Quite an exact number. And here you see, you could prove this by basically the fair game argument that we did before, except here you'd win $26 if you got the right letter, right next letter. So who are the gamblers that are winning by the end? Well, this person who's just got all 11 letters, 26 is on 26 to the 11, but the person who arrived 4 flips ago has got abra, because that's the beginning of abracadabra, is also the end, and he's on 26 to the 4. And actually the last person to arrive just started off on the A here, he got the 26. So the same argument of fair games can prove something like this. Of course, if you tried to do that by simulation, you'd be waiting a very long time. The poor old monkey would have no chance of typing that in his lifetime. He'd be dead. What you'd need is lots of monkeys, right? If you have millions of monkeys, what happens if you have 26 to the 12 monkeys? Maybe then you would see it, right? So there is an important thing, a rare event, something that takes a long time, maybe very rare for one thing, but if there's a lot of attempts going on at the same time, then sooner or later those rare events happen. You can think of mutations in a virus. There's millions of virus particles, they're all trying to mutate. Mutations might be rare, but if there's enough virus particles, eventually they have success and a strange mutation. Okay, so let's go back to our random walk. That was a little bit of homework and guesses for you. So the next thing I want to do is think about scaling a random walk. So again, scaling is a very important thing in probability. We're looking for kind of universal laws and universal theorems that hold in very great generalities, and we're often trying to scale things to see in big pictures, big time, big spatial. Do we get any universal laws that come out? So we start off with our random walk, and so here's our random walk that I did before, or a realization of it. It's a random process. So this is just one particular realization of my heads and tails, gives me this random walk. Apologize for my poor sketch. And now what I'm going to do is I'm going to simulate more random walk, and I'm going to try and look at it, zoom out, look at it from further away. So if you imagine on the same size axis, so I've got the same size axis on the right, I'm going to roughly quadruple the time. So I'm going to run the random walk for 4 times as long. So that's my green box here. I've squeezed into this green box here. So I've roughly got 4 times as much time, but I'm only going to double the space. Yeah, well, yeah, it's not very well drawn. So I'm going to do that procedure, double the time, double the space, but squeeze it into the same size axis. I'm going to do that repeatedly. What happens? Well, what happens is, you remember another one of the cornerstones of probability that actually is really fundamental for much of statistics is the central limit theorem. The central limit theorem tells us if we add up a number of independent, identically distributed mean zero random variables, and we divide by the square root of the variance, then we get something that looks like a normal distribution when we do that with a large number. Add up a large number of mean zero random variables independent, divide by the square root of the variance, it's approximately normal. This is the central limit theorem. So here I'm going to define a new process. Capital N is going to be my scaling. I look at it at some real time t, but that new process y, you think of that as the right hand side, is my original random walk x, but observed for n times t and divided by square root of n. So that's a run time by a factor of n and a change space by a factor of square root. So that's my doubling, quadrupling. They're on different scales. So if I do that scaling procedure, what do I end up with? I end up with something called a Brownian motion in law. So the whole process actually converges to this spiky shaped path, which is got the law of a Brownian motion in the limit. This is known as Donska's theorem, and it's like a souped up central limit theorem. Central limit theorem tells us about one particular time, but the convergence of the random walk is the convergence of the whole process, the whole stochastic process. So it's like a functional central limit theorem. So this is a really nice picture, and it's very robust because the central limit theorem is very robust. So here's a movie, because I'm a bit, my computer skills are limited. I nicked this from Wikipedia, so someone's going to like do me now for like stealing. So this is from Wikipedia, doing that very procedure of scaling. And you see what happens. You start getting this very spiky looking path. This is starting to look like a Brownian motion. Of course, it keeps changing because we're bringing in more and more bits of path, but you can also see it's kind of looking similar. I mean, it's spiky. It settles down and it's pretty spiky, and it just starts looking like a spiky wave moving across. So this is what a Brownian motion looks like in one dimension. Okay. So I'll return to Brownian motion in a second. So I also want to show how random walks are also useful for what I'm going to talk about in the second half. If I get to my second half, I'm doing all right for time-ish. Of course, I haven't timed myself here, so I've no idea whether I'm going to run over. But, hopefully only another couple of hours. No, joking. So now I also want to link my random walk with trees, right? I want to show that random walks can actually be useful for understanding trees, and trees are going to be important for branching processes, as we'll see later. So what the hell is the connection between a random walk that I've been talking about? So here's an excursion of a random walk, this blue line, forget all the other colors. This is like a trajectory of my random walk, starts at the origin, goes positive, goes up 3, down 1, blah, blah, blah. And I'm waiting till it comes back down. So we call this an excursion. It starts at the origin and it stops when it first gets back to the origin. So it's an excursion of a decent length. That's my random walk. What is the connection between this tree and that random walk? Well, let's start with the tree first. So start with the tree here. And I'm going to start on the left-hand side, and I'm going to follow around the contour of the tree. So I'm going to go up. That's an up here. I then go up another 2. Those are the next 2 ups of my random walk. Then I have to come down 1 on that green one. There's my down. Then I have to go up again. That's an up. Down 2. That's the purple down 2. Then up 3. 1, 2, 3. Down, up 1, right? And then down all the way to the bottom. So you can see by following the contour of the tree, I'm either going up or down, and I just change directions and do the same as a function. So this is known as a contour function. And so given a tree, I can produce this contour function, which looks like an excursion of a random walk. It's a very nice link. So a tree can be identified with the random walk, but it works both ways. If I give you the random walk, actually, how do I get the tree? Well, I just look at all the up sections. I just look at the increasing bits, and then I draw horizontal lines across from the bottom of each increasing bit. And that's essentially an identify those 2 points, identify those 2 points, identify those 2 points. And that's actually given me the tree. Another really nice way of doing this is, imagine smearing glue. You could try this practically, it might be horrible. Smearing glue underneath your random walk path and then squishing it together from the side, right? And then let it dry and let it flop apart. Oh, you get the tree, because you'll glue together those two bits, you'll glue together these bits, but those two will be safe, and you get exactly this tree. So there's a link between the excursion of the random walk and a tree. It's going to turn out to be very useful in probability. Now, if we took the scaling limit, right? So now I can do it's a bit of a special scaling limit because I've got to condition on this excursion being large or having large height, but there's a way of taking a scaling limit, and instead of the Brownian motion, we get to what's known as a Brownian excursion. So we've conditioned the Brownian motion to not come back to the origin for a long time. We get a very spiky path. That's that Brownian excursion in the scaling limit, doubling the time square root, but doing a bit of conditioning as well. What happens to the trees in those cases, in that limiting process? Well, we get this really freaky tree that's really complicated called the continuum random tree. I can't even draw it just going vertically. I have to use 2 dimensions to draw the tree because it's so complicated. Somewhere in the middle here's the root, right? But I'm not sure exactly where. I stole these and I didn't get copyright either, so no snitching on me. So this is really nice. So you can describe very complicated random trees with Brownian motions. Okay, so what is a Brownian motion? Maybe I should tell you a little bit more about Brownian motion. So Brownian motion is a continuous process. It has independent normal increments. So for all times st, the change in position bt plus s minus bs is normal naught t. The variance is to do with the length of time, and it's independent of what happened before. So it's got this Markov property. So if you look at the position here and the change over the next bit of time, this increment, this height difference is normal, always normal. It's non-trivial that this thing exists because it's so weird, right? It's Brownian motion. It's a crazy object. It's fractal. If you zoom in, it looks the same. The Brownian motion, if it starts at the origin, actually it visits the origin infinitely often in any tiny interval. It's a bit mental to try and imagine. And it's almost surely nowhere differentiable. I mean, people didn't even think these functions existed for quite a while at the beginning of mathematics. Oh, every function's differentiable. Brownian motion, not differentiable anywhere, basically. But it is a universal scaling limit. And it's quite important because it's got this fair game Martingale property. So it's a very fundamental object, and it is really robust because of the central limit theorem or the generalization of it. So it really appears in a lot of places wherever you've got lots of small increments occurring on the microscopic scale. On the macroscopic scale, you tend to see things that look Brownian motion. So what are some of the applications of Brownian motion? This hideously spiky fractal thing. It's used all over the place. There's just a few: mathematical finance and option pricing, heat and diffusion. This is one of the main things. How does heat flow? It flows exactly. The physicists would write down this second order differential equation. But actually, to solve the heat equation, you just look at the expected value of a function of a Brownian motion. So averages of Brownian motions, they can solve differential equations, and those differential equations pop up in some sense because of the nature of Brownian motion, because of the lots of small contributions adding up. So averages of Brownian motions solve many of the differential equations you see throughout physics and chemistry and biology. Not all of them, but many fit in that category. It also appears in engineering systems where there's noise, if there's you're filtering out dirty signals, or in queuing network approximations. And there's a big theory called stochastic differential equations, which are like souped up differential equations with Brownian random noise in them. There's also all over biological systems, Brownian motions pop up. So for example, if you're looking at the frequency of genes in a large population, then you probably see that the fluctuation in the gene frequency would look a bit like a diffusion, a more complicated version of Brownian motion, but Brownian motion is like the canonical diffusion. So it really does pop up all over the place in applications. It's a very fundamental process. Okay, so the next part of the talk, I want to change tack a little bit, and I want to talk about the trees. So imagine some rats have escaped, and they've made their way onto a nice island, Rangitoto, for example, where they weren't there before. So do they survive? How does the population grow? How fast do they spread to infest the island? And can they be controlled effectively? These will all be basic questions that someone who is interested in a real application would ask. Now, I'm just going to look at some bare theory. I'm going to look at some abstract theory. It's the theory that might underlie more advanced applications. So I'm only looking at very toy models. I always have to emphasize that's theoretical level. But what's the idea of probability is to find order out of the randomness. So if we've got this rats escaping, what might we do to model their population? So the simplest population model, stochastic population model, is known as Galton-Watson process. So we just track the female rats, right? So we don't want to confuse the issue with having to have multiple types at the minute. So suppose we just keep track of the female rats. Each female rat behaves independently. Each female rat gets replaced by a random number of offspring at a constant rate, and we don't care about the males. Males don't matter. We just keep track of the females. And the offspring numbers are all going to be independent with the same probabilities. So we've got what's known as an offspring distribution, where PK would be the probability that we get K female offspring, that female gives birth to K female offspring. And M is the critical quantity. M is going to be the average number of female offspring per birth. So that's the sum, the value times the probability. So this is really the fundamental quantity, the average number of replacements, if you like, for each female. On average, how many replace her when she gives birth? Because then she just gives birth and that's it goes. So what would this process look like if we started with one rat and we tracked it through time at some rate? So this is after some random exponential amount of time. The female rat is replaced by 2 in this case, and then those 2 go on until one of them gives birth. So after some other random amount of time, this one is replaced by 3 offspring. And then we go on a bit longer, then the first offspring gets replaced by 2, and then maybe this one dies, and then so on. Then this one gets replaced by 4, there's a couple more deaths, and then at some point this is the population alive at this time length. So the orange ones are the current population. So this is known as a Galton-Watson process, simple branching process. Okay, so just one realization. It's a random process. If we run it again, we get a different random tree. So what about the growth of the population? So it turns out, if we work out, it's very easy. If we look at the average number of rats alive at time t, then they're actually going to grow exponentially. There's a simple differential equation you can derive from the model, and we get on average e to the beta m minus 1t of them alive at time t. And now what you see from this, the rate doesn't really matter. The thing that really matters is the mean. If the mean is strictly bigger than 1, then the average number grows exponentially. If the mean is 1, it stays the same, that's critical. If the mean is less than 1, it decays. I mean, this is intuitive, right? If you're replaced by on average less than 1, right, your population should be getting smaller each time. If you're being replaced by more than 1 of you, you should be growing. So it's an intuitive result. And indeed, it is the case. The population will die out eventually, almost surely. that's the same as, so with probability 1, that's the same as the number of offspring on average being less than or equal to 1. Even in the critical case, you'll die out. Okay. If you wait long enough, right? That's the catch with elimination. You know, you have to wait. How long do you wait? But it would happen if you waited. So that's an intuitive argument. And in fact, if you do survive, you wouldn't just grow exponentially on average, you would actually grow exponentially. If you look at e to the minus, e to n minus 1t times the total number alive, that converges to a random limit. Actually, this random limit comes from one of those fair games or martingales. So they're popping up all over the place. So a fair game is which you get convergence to a random variable, and that tells you the kind of the constant in front of the exponential growth on survival. If it survives, you could still be unlucky and the first rat could die out. So as we know, it's important in many applications to get M strictly less than 1, whether that is you want to get rid of your mice or your rats, your pest control via putting traps and poisons to reduce the mean, or whether it's vaccination in epidemics, or it's other quarantine or education for the control of infectious disease. Obviously, we've been living this for a while. You can see the relevance where the rats become infected people. So just as a toy model, so this, I have to emphasize, this is a completely toy model, you know, just a back of the envelope calculation. If we looked at an epidemic, and we keep track of the number of infected individuals in each generation, and we wanted to guess what's the rough effect of vaccination. So we assume that if M was bigger than 1 in the first instance, so that would be something where we get an epidemic, we keep growing exponentially. So that's the mean number of new infections per infected individual. So mean number that you pass on the infection to. So suppose we're in this supercritical regime where the mean's bigger than 1, you can get an epidemic, but now vaccinate a proportion B, and suppose the vaccine is 100% protection, then actually what's the effect of that? Well, now you just need to know the mean number of new infections from an infected individual. It gets reduced because before you would meet or pass it on to M on average, but actually a proportion V of those are totally protected, so nothing's going to happen to them. So there's only a proportion 1 minus V of the M that are going to be affected. So you reduce the mean, and so now you just need M 1 minus V less than 1, and so to avoid an epidemic, for the outbreak to die out eventually on its own, you would just need the vaccination proportion to be bigger than M minus 1 over M. So this is like back of the envelope rough computation. So if the mean is 6, for example, you'd need 83%. The mean was A, you need 88%. But it is just a toy model, which is the simplest thing you could ever do. But it gives you some rough ideas, right? So these are not unreasonable numbers, but it's a very simple, crude estimate, but not bad. So you could do the same if you wanted to do a more sophisticated model, slightly more. You say, well, okay, you vaccinate proportion B, but maybe it's not 100% protection. Maybe that reduces, it only protects with probability P. If it's only 90% effective, 10% people can still get ill, but otherwise no effect at all. So in that case, the proportion of protected people is well, you've got to be vaccinated and be lucky that it works. So it's V times P is the proportion that are protected and it works. So the proportion that are not protected is 1 minus VP. So now you would need M times 1 minus VP to be less than 1, for example. So if you've got 90% vaccinated and it's 90% effective and 10% no effect at all, of course, it's just like a very toy model again, then you would want to keep M less than 5.3 one way or another. If the vaccination rate got up to 95% but the protection was down at 70, then you'd need the mean to be strictly less than 3. So you can start to see how you know, how other measures become important for controlling M as well as vaccination and its efficacy. But again, it's a toy model. So I'm not making any claims about this. It's just the simplest thing you would ever do. So actually what you might want to do next, you know, is you start with the easy and you work up more complicated models. Maybe the next thing you want to do is have a two-type model. So you have two different types of individual, vaccinated people and unvaccinated people, and they behave differently. Maybe the vaccinated people, they don't pass it on as not as infectious, so they have different means. So you could do more complicated things. So in fact, there's a generalization for multi-type branching processes where now the mean being less than 1 is replaced by the largest eigenvalue of a matrix. So you need a mean matrix. You need to look at the mean number that type I individual gives birth, the mean number of type J's that an I individual gives birth to. You stick those in a matrix. You know, so matrices play an important role in those more advanced multi-type models. So you've got much more flexibility, you can do much better modeling, and there's a big theory of multi-type branching processes that goes along to help this. So now I'd say I'm just a theory guy working at the, you know, far away from the applications, but as you probably aware that these stochastic branching process models have been used extensively by Poonawala Tatini, the TPM team, as part of our NZ COVID modeling. So they really are used. So you have many types, you have different, break it down, and then you get estimates. So very sophisticated models can give very, very good detailed estimates and predictions about what's going to happen, and played an important role in keeping us safe over the last couple of years. Okay, so how am I doing for time? So I've got about 8 minutes left. Bit behind. I thought I'd be on schedule. Okay, so there's a couple of other things I'd like to squeeze in. So the next thing I want to just talk a little bit about is genealogies. So suppose we got one of these branching, these population processes growing, and suppose we observe it and run it for time t, and then these orange ones are the ones that are alive. So these red ones died along the way. And we might ask, well, what does the ancestral family tree look like if I took a sample of individuals from the current population? So instead of looking at all of the individuals and the whole tree, suppose I just take a sample of these pink ones. So I just choose 4 out of the population of 8. And if I only look at those 4 individuals, how are they related? What does their family tree look like? Well, I just have to trace back along the past, right, and see when they first have common ancestor. These 2 had a common parent, common ancestor there, and then these 3 all had a common ancestor here. So this is time on the x-axis, and this one had the common ancestor with all the others back at the beginning, and then this was the original birth of the original ancestor of everybody. So I'm interested in that, just in that family tree of the sample, which I can draw up a bit more neatly. It's the same, doesn't matter about those vertical kinks. So this is the ancestral family tree of the sample from the bigger process. So of course, to answer this question, you'd need to first know, well, what model am I using? What's the population model? For example, the Galton-Watson population model I was talking about earlier. So you need an underlying model. You'd also need a sampling mechanism. So are you going to sample uniformly at random? Are you going to sample from within the same family group or whatever? Often we'll try and do uniform sampling at a fixed time t. And so what might you observe? What might you expect to see if you looked at the most recent common ancestors? Say you just picked 2 individuals. Well, if it's a huge population, so if it's in this supercritical case and it runs for a long time where there's exponential growth, you'd expect to have a massive population. So if you chose 2 individuals, they're probably not related, right? They'd be related way back at the start, distant relations. On the other hand, if it's subcritical, So if it's trying to die out, if you condition on surviving a large time, because it needs to be alive for you to sample it, so if you condition on survival, actually it's trying to die out all the time. So there's probably just a few individuals alive. So if you pick 2 of them, they're probably closely related. So this is like in the endangered species world. So if we're thinking of looking at taking a sample from an endangered species, it's struggling to survive, it's a small population, individuals are probably quite closely related. And indeed, probability can prove these kind of intuition in a more detailed way, and actually can show that the time of the most recent common ancestor converges in law for a Galton Watson, or the time back from the end converges in law. So those are some results you can get in the subcritical case. If you looked at the genealogy more generally and at a tree of criticality, so this is quite a good, often probabilists look at critical branching where m equals 1. So it would die out eventually, but if you condition on being alive, you actually tend to get quite a large population, a large stable population with a little bit of fluctuations. And if you took a sample from that large population conditioned to survive, what would it look like? Well, you can describe that genealogy very nicely. You can find all the coalescent times, you can describe the shape of the tree. And this, you know, even for the Galton Watson at criticality, this was unknown, it wasn't known till recently, where myself and some colleagues used some cutting edge probability theory to solve that problem. And this is a bit related to, this case is related to sampling from that crazy tree from the scaled random walk. So there's a link back to our random walk, a scaled random walk with the Brownian excursion. The Brownian excursion was a representation of this crazy continuum random tree. And here you kind of sample randomly from this massive population. And what does the family tree look like of those 5 individuals? You can describe it. So there's some of the kind of questions that you can answer. So what are the kind of applications to this? Well, one of the big applications is phylogenetics. If you're looking at, so understanding the probability behind these genealogical trees is important for modeling in phylogenetics and speciation. So you might be modeling how species evolve and new species split apart. So for example, you might add mutations might be occurring along the branches of the tree, and that might help you identify give you information about the tree. Basically, if you know about some of the mutations by doing DNA testing, then you're getting information about how people are related, whether they carry the same mutations or not. You could do this for the viruses, for example. So how does probability and statistics interplay here? So this is one of the common ways that probability, what's the probability, that the kind of stuff that I do, it's all working out, given the model and the parameters, I choose the model, I set up the parameters, I fix them, and then I work out what's the probability I get this tree, what's the probability I get this coalescent structure, this genealogical, given I know the parameters. But actually in the real world, you're given the data, you know the data, and you want to know what are the parameters. Is the endangered species recovering? Is its population growing now? Or is it dying out? Or you want to know, you know, what the R naught is, the R effective is in your epidemic. So you want to know about the parameters given the data. Of course, Bayes' theorem, another classic early probability theorem, tells you how to swap the orders of conditional probability. So the probability of the parameters given the data is proportional to the probability of the data given the parameters that you can get from probability times some prior distribution about the parameters. So that's, you know, so that's where the statistics and probability have a bit of interplay. And of course, this is just the beginning. So I'm just doing the noddy theory at the beginning. So the true applied people have been using sophisticated models for phylogenetic analysis, for example, of the COVID. So that's teams in New Zealand, and they get some fancy phylogenetic tree. So that's all using some much more sophisticated and specialized models further down the line. Okay, I think I'll stop there, skip my last slide because I'm over. Thank you.